July 12, 1943. The sun-scorched plains north of Gela, Sicily. Sergeant Frank Morrison of the 2nd Armoured Division tracked a distant shape through his periscope as his Sherman lurched forward across broken volcanic rock. The shape resolved into an Italian Semovente da 75/18, its low casemate unmistakable against the treeline. Morrison's gunner already had the 75mm gun swinging toward the target, the hydraulic traverse whining smoothly even as the Sherman bounced over uneven ground. What Morrison didn't fully appreciate at that moment was that his tank possessed a technological advantage the Italian crew could not match. A single-axis gyrostabilizer, primitive by later standards but revolutionary for 1943, kept his gun pointed roughly where his gunner aimed it despite the Sherman's movement. The Italian vehicle had no such system. Its crew would need to halt completely, carefully aim through static optics, and hope their target remained stationary long enough for an accurate shot. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. This seemingly modest technological difference would prove far more consequential than armor thickness or raw firepower in determining which crew would survive the next 60 seconds. The story of how American industry embedded gyrostabilization into every Sherman tank begins not on Sicilian battlefields, but in Massachusetts research facilities and Detroit production lines, where engineers worked to solve a problem that most armies believed unsolvable: how to aim a tank gun accurately while moving. Spring 1941. Aberdeen Proving Ground, Maryland. Test engineers from Westinghouse Electric and the United States Army Ordnance Department gathered around an experimental M3 medium tank modified with a prototype stabilization system. The mechanism, officially designated the Gyrostabilizer M1, represented 3 years of collaborative development between military requirements officers and civilian engineering firms. The American military had recognized the value of fire-on-the-move capability as early as 1938, when crude stabilization experiments were conducted on the experimental M2A2E3 light tank. Those early tests produced disappointing results, but they established the fundamental principle: a tank that could maintain weapon orientation while moving possessed significant tactical advantages over vehicles requiring complete stops before firing. The challenge was formidable from an engineering perspective. A tank gun mounted in a turret experiences constant movement in multiple axes as the vehicle traverses uneven terrain. Pitch, roll, and yaw combine with the turret's own rotation to create complex displacement patterns that simple mechanical solutions could not address. The Westinghouse solution focused on vertical stabilization only, accepting that horizontal traverse would remain manually controlled. A mechanical gyroscope, spinning at high velocity, maintained orientation relative to true vertical, regardless of hull movement. This gyroscope fed position information to a servo motor that continuously adjusted gun elevation to compensate for pitch changes caused by the hull moving over terrain. The system was not designed to allow accurate shooting while moving at high speed. The 1941 technology could not achieve that level of precision. Instead, the gyrostabilizer served a more modest but tactically valuable purpose. It kept the gun approximately on target during movement, allowing the gunner to maintain sight picture and reducing the time needed to achieve firing accuracy after the tank stopped. Tests at Aberdeen during spring and summer 1941 demonstrated measurable advantages. Tanks equipped with stabilization could halt, acquire final aim, and fire approximately 2 to 3 seconds faster than unstabilized vehicles whose guns wandered significantly off target during movement, require complete relaying before shooting. This time advantage, measured in seconds, translated directly into survival probability during armored engagements. The crew that fired first often won the engagement. The crew forced to spend additional seconds re-aiming after stopping presented an easier target. The United States Army, observing these test results and studying early tank warfare lessons from Europe and North Africa, made a consequential decision. The stabilization system would be standard equipment on the upcoming M4 Sherman medium tank, not optional equipment for specialized units, but factory installed on every production vehicle. This decision reflected American industrial philosophy and military thinking that differed fundamentally from European approaches. German and Italian tank designers prioritized other characteristics, accepting that tanks would fire from static positions after careful aiming. American designers, influenced by cavalry traditions emphasizing mobility and by automotive industry experience with power-assisted controls, believed that fire control systems should work for the crew rather than requiring the crew to work around system limitations. Production of M4 Sherman tanks began at 11 separate manufacturing facilities between February 1942 and January 1943. Lima Locomotive Works, Pressed Steel Car Company, Pacific Car and Foundry, and 8 other contractors tooled up to produce identical vehicles incorporating the Westinghouse Gyrostabilizer as standard equipment. Each Sherman leaving these production lines carried the stabilization mechanism, regardless of whether crews would learn to use it effectively. The industrial capacity to equip every tank demonstrated American manufacturing scale that Axis powers could not match. Germany and Italy struggled to produce adequate numbers of tanks with basic systems. America mass-produced advanced fire control technology as standard equipment. The gyrostabilizer itself was mechanically complex, but operationally straightforward. A vertical gyroscope, mounted below the gun and spinning at approximately 10,000 revolutions per minute, sensed changes in elevation angle. An electrical servo motor responded to gyroscope signals by driving the gun elevation mechanism through reduction gearing. The gunner controlled this system through a switch on his control handle. With stabilization engaged, the servo motor continuously adjusted gun position to maintain the elevation angle the gunner selected, compensating for hull pitch as the tank moved. With stabilization disengaged, the gun responded only to manual controls. Training materials distributed to Sherman crews in 1942 and 1943 emphasized proper stabilizer employment. Field Manual 17-12, Tank Gunnery, provided specific guidance on when stabilization proved most useful. The manual explained that firing the 75mm gun while moving remained inaccurate and wasted ammunition. Crews should use stabilization to maintain approximate aim during movement, then halt briefly for final laying before firing. At ranges below 600 yards, against large targets, crews might fire while moving in emergency situations, but this represented desperate tactics rather than preferred employment. The reality of combat employment proved more complex than training manuals suggested. Many crew commanders, unfamiliar with the stabilization system's proper use and unaware of its tactical value, simply switched it off and never engaged it again. Some units, receiving hastily trained replacement crews after casualties, lost institutional knowledge about stabilizer operation entirely, but units that maintained proficiency and used the system correctly gained measurable advantages. British evaluations of Lend-Lease Sherman tanks in North Africa during 1942 and 1943 noted that stabilization, while not permitting accurate fire on the move, significantly reduced engagement time when crews operated it properly. A British Armoured Corps evaluation from autumn 1943 stated that crews trained to work with the stabilizer rather than fighting against it could engage targets approximately 3 seconds faster than crews in unstabilized vehicles. In tank versus tank engagements at ranges between 500 and 1,000 yards, 3 seconds often determined survival. Meanwhile, Italian tank and self-propelled gun designers pursued entirely different technical priorities. Italian military doctrine, shaped by limited industrial capacity and different tactical thinking, accepted that armored vehicles would engage from prepared positions after careful aim. The Italian Regio Esercito had entered World War II with an armored force built primarily around light tankettes and obsolescent medium tanks. The Fiat L3 tankette, essentially a machine gun carrier with minimal armor, formed the bulk of Italian armored strength in 1940 and 1941. These vehicles could not engage enemy tanks effectively and provided only mobile fire support for infantry. Recognition of this inadequacy led Italian designers to develop the Semovente series of self-propelled guns. Rather than building fully rotating turrets like the Sherman, Italian engineers mounted fixed casemate guns on modified tank chassis. This approach eliminated the complexity and weight of turret traverse mechanisms while providing heavier armament than existing Italian tanks could carry. Colonel Sergio Bellese, who had designed the Obise da 75/18 Modello 34 mountain howitzer, proposed adapting this weapon for armored vehicle use. His design mounted the howitzer in a low, fixed superstructure on the chassis of the M13/40 medium tank. The first Semovente prototype, completed in February 1941, demonstrated the concept's feasibility. The vehicle provided mobile heavy firepower at relatively low production cost, using existing tank components and proven artillery pieces. Italian authorities, operating under severe industrial constraints, approved production. The Semovente da 75/18 entered service with Italian armored units in early 1942. Approximately 288 vehicles were eventually produced using M13/40, M14/41, and M15/42 chassis between 1941 and 1943. The 75mm howitzer, mounted on a simple spherical support in the forward casemate, provided manual traverse of approximately 34 degrees and elevation from -12 to +22 degrees. The gun layer adjusted aim using hand wheels that mechanically rotated the weapon on its mounting. Fire control consisted of basic optical sights with no power assistance, no stabilization, and no sophisticated range-finding equipment. The gunner looked through a telescopic sight, manually adjusted elevation and traverse using hand wheels, and estimated range based on experience and visual assessment. This system required the vehicle to halt completely before engaging targets. Any movement, even minor vibration from the engine, disrupted aim through the telescopic sight. Accurate shooting demanded a stable platform and careful manual laying of the gun onto the target. Italian crews trained accordingly. Semovente doctrine emphasized selecting good firing positions with clear sight lines, moving into position deliberately, halting completely, and engaging targets with carefully aimed fire. Movement and shooting were sequential activities, never concurrent. The Semovente proved surprisingly effective within these operational limitations. The 75mm howitzer, firing effetto pronto-shaped charge ammunition, could penetrate 80mm of armor at 500 meters. This gave Semovente the capability to defeat British Crusader tanks and even American M4 Shermans under favorable circumstances. At the Battle of Gela in June 1942, Semovente da 75/18s of the Ariete Division engaged British armour successfully from prepared positions. Operating in the defensive role their design intended, carefully positioned and firing from static emplacements, the Italian self-propelled guns achieved favourable kill ratios against attacking British tanks, but this success depended entirely on favourable tactical circumstances. The Semovente required time to position, time to aim, and enemy cooperation in providing stationary or predictable targets. Any scenario demanding rapid engagement of moving targets or fire while maneuvering exposed the vehicle's limitations. German assessments of Italian armoured vehicles, documented in captured Wehrmacht reports from 1942 and 1943, acknowledged the Semovente's firepower, while noting its tactical inflexibility. German liaison officers serving with Italian armoured units observed that Semovente performed well in prepared defensive positions, but struggled in fluid mobile warfare. A Wehrmacht report from August 1942, discussing Italian armoured forces in North Africa, stated that Italian self-propelled guns possessed adequate weapons for anti-tank combat, but required careful positioning and could not effectively engage targets while moving. The report contrasted this with German Sturmgeschütz assault guns, which, while also lacking turrets, incorporated superior optics and more sophisticated fire control systems. The fundamental difference lay not in weapon caliber or armor thickness, but in fire control philosophy and technological implementation. German assault guns, though also casemate mounted, featured advanced Zeiss optics, precise range-finding equipment, and mechanical systems designed for rapid target engagement. Italian Semovente relied on simpler optical sights and entirely manual fire control. American Sherman tanks went further, incorporating powered turret traverse and gyrostabilization that transformed the relationship between movement and shooting. While Sherman still fired most accurately from stationary positions, they maintained the capability for rapid engagement after brief movement and could even risk firing while moving in desperate circumstances. These technical differences reflected broader patterns in industrial capacity and design philosophy. Italy's limited manufacturing base forced designers to prioritize simplicity and production economy over technical sophistication. Germany's more advanced industry supported complex engineering solutions, but struggled with mass production. America's enormous industrial capacity enabled both technical sophistication and overwhelming numerical production. By summer 1943, these divergent approaches faced direct battlefield comparison. Operation Husky, the Allied invasion of Sicily, brought American Sherman tanks into combat against Italian Semovente under conditions that starkly revealed the consequences of different fire control technologies. The American invasion force included the 2nd Armored Division, equipped with approximately 250 M4 and M4A1 Sherman tanks. These vehicles, fresh from American factories, incorporated standard production gyrostabilizers and hydraulic turret traverse. Crews had received varying degrees of training on stabilizer employment, with some units proficient and others barely aware of the system's existence. Italian defenders on Sicily deployed Semovente da 75/18 self-propelled guns as part of their mobile reserve. The Ariete II Division and various independent Semovente groups positioned their vehicles to defend against expected beach landings. The tactical situation favored neither side inherently. Americans faced the challenge of amphibious assault against prepared defenses, while Italians operated in familiar terrain but with numerical disadvantage and minimal air support. What tipped the balance, beyond numerical superiority and Allied air dominance, was the capability gap in mobile gunnery. Sherman crews could move, halt briefly, and engage targets with minimal delay. Semovente crews required complete stops, careful aiming, and static firing positions to achieve accuracy. The Battle of Gela, fought July 10th through 14th, demonstrated these technical differences under brutal combat conditions. Italian armored counterattacks, including Semovente moving toward American beach positions, encountered Sherman tanks that could respond faster and shoot more accurately after movement than Italian vehicles designed for static defense. Sergeant Morrison's engagement north of Gela on July 12th typified hundreds of similar encounters. His Sherman, moving at approximately 15 miles per hour across rough ground, maintained approximate aim on the distant Semovente throughout the approach. Morrison's gunner, trained on stabilizer use, kept the reticle roughly on target despite the hull's pitching motion. The Italian Semovente crew, spotting the approaching Sherman, faced a tactical choice: halt immediately and attempt to engage first, or continue movement seeking better position. They chose to stop, knowing their fire control system demanded it. The halt itself consumed seconds. Engine noise decreased, vibration settled. The gun layer could finally see clearly through his telescopic sight. He began manual traverse, cranking the hand wheel to bring the gun toward the Sherman's position. Morrison's Sherman slowed but never stopped completely. The gyrostabilizer held elevation steady. The gunner made final corrections, compensating for the vehicle's residual movement and the target's range. The commander gave the fire command. The 75mm gun fired. The tungsten core armor-piercing round, traveling at over 2,000 feet per second, struck the Semovente's frontal casemate. At 600 yards range, the shell penetrated the 50mm armor and detonated stored ammunition. The Italian vehicle exploded, turret lifting slightly from internal pressure before settling back onto the hull. Morrison's Sherman continued forward, already seeking the next target. This engagement lasted perhaps 20 seconds from initial sighting to destruction. The technical advantage provided by gyrostabilization, measured in seconds of engagement time, determined the outcome as decisively as armor penetration or gunnery skill. The pattern established at Gela repeated across Sicily throughout July and early August 1943. American armored units, advancing inland from beachheads, encountered Italian defensive positions, incorporating Semovente self-propelled guns positioned to cover key terrain. These engagements consistently demonstrated that static defensive doctrine, no matter how carefully executed, surrendered initiative to attackers possessing mobile fire control. Italian crews could achieve excellent accuracy from prepared positions when conditions allowed deliberate aiming, but American tank crews, using gyrostabilization to maintain approximate aim during movement, seized tactical initiative by firing first after rapid advances. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Field reports from the 2nd Armored Division, compiled during the Sicily campaign, documented engagement sequences that revealed the stabilizer's combat value. Tank commanders reported that even crews initially skeptical of the gyrostabilization system recognized its usefulness after experiencing combat against Italian armor. One after-action report from Company C, 67th Armored Regiment, described an engagement on July 23 near Comiso. 3 Shermans, advancing across open ground toward Italian positions, maintained formation movement while engaging 2 Semovente, emplaced behind earthworks. The Italian vehicles opened fire first from static positions, achieving 1 hit that damaged but did not penetrate a Sherman's frontal armor. The American tanks, rather than halting completely to return fire, slowed to approximately 5 miles per hour, while their gunners used stabilization to maintain aim. All 3 Shermans fired within 4 seconds of receiving the initial Italian shot. 2 of 3 American rounds struck Italian vehicles, destroying 1 Semovente and forcing the crew of the second to abandon their position. The engagement demonstrated tactical principles that would remain relevant throughout the war. Vehicles capable of shooting accurately shortly after movement could seize and maintain initiative. Vehicles requiring complete stops before engaging surrendered tempo control to enemies who could respond faster. Lieutenant Colonel Creighton Abrams, commanding the 37th Tank Battalion at the time, recognized these patterns and emphasized stabilizer training for his crews. Abrams, who would later rise to Army Chief of Staff and have the M1 Abrams main battle tank named in his honor, understood that technological advantages meant nothing unless crews employed them properly. Abrams instituted training protocols requiring gunners to practice firing with stabilization engaged, teaching them to work with the system rather than fighting against it. His battalion's after-action reports from Sicily showed consistently shorter engagement times compared to units whose crews disabled their stabilizers. The Italian perspective on these engagements, documented in captured unit records and post-war interviews with surviving crew members, revealed frustration and tactical helplessness. Italian commanders understood their vehicles' limitations but lacked industrial capacity to address them. A report from the Raggruppamento Tattico Schreiber, an Italian combat group that fought in Sicily, noted that American tanks demonstrated superior ability to engage targets rapidly after movement. The report attributed this partly to better crew training but also acknowledged that American vehicles appeared to possess fire control systems more sophisticated than Italian equipment. German liaison officers attached to Italian units provided more technically detailed assessments. A Wehrmacht report from late July 1943, written by a German tank officer observing Italian armored operations, specifically mentioned American tank stabilization. The German officer noted that American Sherman tanks appeared capable of maintaining gun orientation during movement, suggesting some form of stabilization mechanism. He contrasted this with Italian self-propelled guns that required complete stops before accurate fire. The report recommended that German forces prepare for American tanks with stabilized guns when they eventually faced them in Italy proper. These German observations proved prescient. When Allied forces crossed from Sicily to mainland Italy in September 1943, Sherman tanks equipped with gyrostabilizers encountered German armor that, despite superior gun power and armor protection, lacked any stabilization system. But before examining those later engagements, the Sicily campaign's conclusion revealed another dimension of the stabilization advantage. As Italian resistance collapsed and units retreated toward Messina, American armored forces conducted pursuit operations that showcased mobile gunnery's value. Pursuit operations demanded that tanks move rapidly while remaining ready to engage enemy rearguards instantly. Shermans with operational stabilizers could advance at speed, maintain approximate aim on potential targets, and engage quickly when rearguard positions revealed themselves. This capability proved invaluable for sustaining pursuit momentum. Italian Semovente, designed for deliberate positional warfare, could not effectively perform rearguard missions requiring rapid displacement and engagement. Units attempting to establish successive defensive positions found themselves engaged and destroyed before completing their setup. The 10th Raggruppamento Semovente, attempting to cover the Italian withdrawal toward Messina in early August, lost 14 of 16 self-propelled guns over 3 days of fighting. American after-action reports attributed these losses partly to air attack, but noted that ground engagement by Sherman tanks accounted for most Italian vehicle destructions. The fundamental asymmetry was clear. American tanks could engage Italian vehicles effectively during movement. Italian vehicles could not reciprocate. This one-sided capability determined engagement outcomes before shots were fired. The technical comparison extended beyond the immediate tactical level to industrial and doctrinal implications. American production of gyrostabilizers for Sherman tanks represented a massive industrial commitment that Axis powers could not match. Westinghouse Electric alone produced thousands of stabilization units monthly by mid-1943. The Oil Gear Company manufactured hydraulic turret traverse systems at similar scale. These components, incorporated into every Sherman as standard equipment, represented manufacturing, sophistication, and capacity that Italy and Germany could not replicate. Italian industry struggled to produce adequate numbers of basic armored vehicles. Adding complex fire control systems to existing designs exceeded available engineering resources and manufacturing capacity. Italian designers focused on maximizing firepower and protection within severe industrial constraints, accepting that fire control would remain manual and simple. German industry, while more capable than Italy's, faced similar resource allocation dilemmas. German tank designers prioritized gunpowder and armor thickness, believing that technical superiority in those areas compensated for lack of stabilization. This belief proved partially correct. German heavy tanks could destroy Shermans at ranges where stabilization provided no advantage, but it ignored the tactical reality that most engagements occurred at intermediate ranges, where stabilization significantly affected engagement time. The German decision to forego stabilization development reflected doctrinal assumptions about tank warfare. German doctrine emphasized prepared defensive positions and long-range gunnery, scenarios where stabilization provided limited value. This doctrine worked effectively on the Eastern Front against Soviet forces whose tanks also lacked stabilization. But against American forces employing combined arms tactics with stabilized tanks, German doctrine encountered problems. American tank units advanced under artillery support and air cover, forcing German tanks into hasty engagements where stabilization advantages manifested clearly. Albert Speer, Germany's Minister of Armaments and War Production, observed American Sherman tanks during his inspection tour of Italy in October 1944. In his post-war memoir Inside the Third Reich, Speer noted that Sherman capabilities impressed German commanders, particularly the tank's cross-country mobility and apparent ease of operation. Speer's observations, while not specifically mentioning gyrostabilization, acknowledged that American tanks possessed operational characteristics German designs lacked. He attributed this to American automotive industry experience applied to military vehicle development, a perceptive assessment that identified the core advantage. American tank designers, drawn from automotive industry backgrounds at General Motors, Ford, and Chrysler, approached tank design as an automotive engineering problem. They incorporated power steering, power-assisted controls, and stabilization systems routinely used in commercial applications. These features, standard in American industrial practice, represented advanced technology when applied to military vehicles. Italian and German designers, working in different industrial contexts with different priorities, produced vehicles optimized for other characteristics. Italian designs prioritized production simplicity. German designs prioritized individual vehicle combat power. American designs prioritized operational effectiveness across diverse tactical scenarios. The battlefield results validated the American approach. Sherman tanks, individually inferior to German Panthers and Tigers in gunpowder and armor, proved operationally superior through better reliability, easier crew training, and more effective fire control systems. The Gyrostabilizer, though primitive by later standards and often misunderstood by crews, exemplified this philosophy. The system provided a small but measurable tactical advantage that, multiplied across thousands of tanks and hundreds of engagements, significantly affected combat outcomes. By September 1943, when Allied forces landed on the Italian mainland at Salerno and crossed the Straits of Messina into Calabria, Sherman tanks had compiled an extensive combat record demonstrating stabilization's value. Training materials distributed to new armored units emphasized proper stabilizer employment based on Sicily campaign lessons. Technical Manual 9-759, published in October 1943, incorporated battlefield feedback about stabilizer use. The manual clarified that stabilization's purpose was maintaining approximate aim during movement, not enabling accurate fire at high speed. Crews should engage stabilization when moving toward expected contact, maintain it during combat movement, and use it to reduce engagement time after stopping. The manual also addressed common crew mistakes. Many gunners, unfamiliar with stabilization, attempted to manually correct aim while the servo motor was actively compensating for hull movement. This created a feedback loop where gunner and stabilizer fought each other, producing worse results than no stabilization at all. Proper technique required the gunner to place the reticle on target and allow the stabilizer to maintain that orientation, making only small corrections for target movement or range changes. Gunners who learned this technique, essentially cooperating with the automation rather than overriding it, achieved significantly better results. These training improvements, distributed throughout American armored forces in late 1943 and early 1944, increased stabilizer effectiveness. Units landing in Italy for the continuing campaign possessed better institutional knowledge about fire control system employment than earlier forces. The Italian campaign from September 1943 through May 1945 provided extensive additional data about stabilization advantages. While Italian armored forces had largely ceased organized resistance after the September armistice, German forces defending Italy employed captured Italian vehicles, including Semovente. Wehrmacht units using Semovente encountered the same fire control limitations Italian crews had faced. German tankers, accustomed to sophisticated optics but no stabilization in their own vehicles, found Italian self-propelled guns particularly frustrating. The combination of fixed casemate guns and manual fire control without stabilization made rapid engagement extremely difficult. A German tank officer's diary, captured in January 1944 near Cassino, expressed frustration with a Semovente da 75/18 his unit had pressed into service. He noted that the vehicle possessed adequate firepower, but required excessive time to aim accurately. He contrasted this unfavorably with his previous vehicle, a Panzer IV, which had superior optics and faster manual traverse. This comparison highlighted that even without stabilization, German fire control systems provided advantages over Italian equivalents. German Zeiss optics delivered clearer target identification at longer ranges. German turret traverse mechanisms, though manually powered, operated more smoothly and precisely than Italian systems. These incremental improvements added seconds to engagement speed, but German vehicles still required complete stops before accurate fire, just as Italian vehicles did. Neither possessed gyrostabilization. Both surrendered the tactical initiative to Sherman crews who could engage targets more rapidly after movement. The cumulative effect of these small tactical advantages determined operational outcomes across the Italian campaign. American and British forces, advancing up the Italian peninsula, encountered fierce German resistance, exploiting mountainous terrain that favored defense. But even in terrain advantageous to defenders, attackers with superior fire control could force engagements on favorable terms. Sherman tanks, operating in terrain that limited their mobility advantages, still benefited from stabilization when engaging defensive positions. The ability to move between covered positions, stop briefly, and engage accurately before defenders could respond effectively proved valuable in close-terrain fighting, where ranges rarely exceeded 600 yards. The technical advantage, measured in seconds per engagement, accumulated across thousands of engagements to produce measurable operational effects. American armored divisions advancing through Italy logged higher vehicle availability, lower crew casualties per engagement, and faster advance rates than would have been achieved with unstabilized tanks. Quantifying these effects precisely proves difficult because no controlled comparison existed. American forces did not field identical units with and without stabilization to measure performance differences directly. But indirect evidence from engagement reports, casualty statistics, and advance rates suggests stabilization contributed meaningfully to tactical effectiveness. A study conducted by U.S. Army Ordnance in late 1944 attempted to quantify stabilizer value by comparing engagement times reported in after-action reports. The study found that Sherman crews using stabilization engaged targets an average of 2.8 seconds faster than the engagement time theoretically required for unstabilized tanks to aim from rest. This time advantage, small in absolute terms, translated to approximately 40% faster engagement cycles. In tank versus tank combat, where first shot often determined survival, this represented substantial tactical value. The study also documented that many crews still disabled their stabilizers or used them improperly, suggesting that actual combat effectiveness fell short of potential capability. Even with imperfect employment, stabilization provided measurable advantages. With better crew training, the advantages would have been larger. The contrast with Italian Semovente could not have been starker. Italian vehicles, trapped by design choices made under industrial constraints, could never achieve stabilized fire control without complete redesign. The manual fire control systems installed in Semovente represented the best solution available given Italian manufacturing limitations, but they could not match American power-assisted stabilized systems regardless of crew skill or tactical employment. This technological gap reflected deeper industrial realities that determined the war's outcome. Italy entered World War II with industrial capacity roughly 1/10 of American levels. This disparity manifested not just in production numbers, but in the sophistication of standard equipment. American industry routinely incorporated power assistance, electrical controls, and automated systems into military equipment, because these technologies were mature and available from civilian applications. Italian industry, lacking equivalent civilian, automotive and electrical sectors, could not transfer similar capabilities to military production. The Semovente's manual fire control, simple telescopic optics, and hand-cranked gun laying represented appropriate solutions for Italian industrial reality. More sophisticated systems would have delayed production, increased costs, and complicated maintenance without proportional combat value, given Italian operational doctrine. But appropriate for Italian circumstances did not mean competitive against American technology. The Sherman's Gyrostabilizer, hydraulic turret traverse, and power-assisted controls delivered combat advantages that Italian vehicles could not match. German post-war analysis of tank design lessons identified American fire control superiority as a significant factor in Allied operational success. A 1947 study by former Wehrmacht tank officers noted that American tanks, while inferior in armor and gun power to German heavy tanks, possessed better operational characteristics, including superior crew ergonomics and more effective fire control for typical engagement scenarios. The study specifically mentioned gyrostabilization as an American innovation that German designers had not prioritized. German tank development focused on increasing gun power and armor thickness to maintain qualitative superiority over numerically superior enemies. This approach produced individually powerful vehicles that could not be manufactured in sufficient quantities and lacked refinements that improved crew effectiveness. American tank development, by contrast, prioritized reliability, ease of production, crew training efficiency, and operational effectiveness. Gyrostabilization exemplified this philosophy perfectly. The system cost relatively little per vehicle, required minimal crew training, and provided measurable tactical advantages across diverse engagement scenarios. The legacy of World War II tank stabilization extended far beyond the conflict in itself. Every modern main battle tank incorporates sophisticated stabilization in multiple axes, allowing accurate fire while moving at high speeds across rough terrain. This capability, now taken for granted, traces its origins directly to the primitive single-axis gyrostabilizer developed for the M4 Sherman. Soviet tank designers, studying American technology through Lend-Lease Shermans delivered to the Red Army, recognized stabilization's value. The T-54 tank, introduced in 1947, featured a stabilization system clearly influenced by American designs. Subsequent Soviet tanks incorporated increasingly sophisticated stabilization, making it standard in Warsaw Pact forces. British tank designers developed two-axis stabilization for the Centurion tank in 1948, enabling accurate fire while moving. This capability gave British armour significant advantages during Cold War confrontations. American designers, ironically, abandoned stabilization in immediate post-war tank development. The M46, M47, and M48 tanks lacked stabilization systems, representing a regression from Sherman capabilities. Not until the M60 tank in the 1960s did American armour regain stabilized fire control. This temporary abandonment reflected institutional forgetting about technology's combat value. The officers who designed post-war American tanks had not experienced Sherman stabilization's tactical advantages directly. They prioritized gunpowder and armor, neglecting fire control refinements that combat veterans understood mattered. The M60 ultimately received add-on stabilization in the early 1970s after Vietnam experience demonstrated its importance. The M1 Abrams tank, introduced in 1980, incorporated sophisticated two-axis stabilization from initial design, enabling accurate fire at high speeds. Modern tank stabilization has evolved far beyond the primitive gyroscopic systems of 1943. Contemporary systems use laser gyroscopes, digital computers, and complex servo mechanisms to maintain aim within milliradians, while moving at maximum speed across any terrain. Gunners can engage targets accurately while the tank travels at 40 miles per hour over rough ground, something impossible with 1940s technology. But the fundamental principle remains identical. Stabilization maintains weapon orientation despite vehicle movement, enabling faster engagement and more accurate fire under conditions where unstabilized systems would fail. This principle, first implemented operationally in the M4 Sherman, now defines modern armored warfare. The Italian Semovente, with its manually laid gun and simple fire control, represents an evolutionary dead end in tank destroyer design. Modern self-propelled guns universally incorporate stabilization, powered traverse, and sophisticated fire control computers. The concept of a fixed casemate fighting vehicle with entirely manual gun laying has disappeared from military inventories worldwide. This evolution validates the American approach of incorporating available technology into standard production vehicles, rather than accepting limitations justified by doctrine or industrial constraints. The M4 Sherman's gyrostabilizer, though primitive and often misunderstood by crews, pointed toward the future of armored warfare more accurately than any other tank fire control system of World War II. July 12, 1943, north of Gela. Sergeant Frank Morrison's Sherman rolled past the burning Semovente, already scanning for additional targets. Morrison did not know the technical specifications of his gyrostabilizer, could not explain how the servo motor maintained gun elevation, and had only basic understanding of why stabilization helped his crew survive. He knew only that when his tank moved, the gun stayed roughly where his gunner aimed it. When they needed to shoot quickly, the stabilization let them engage faster than enemy vehicles that required longer aiming periods. In tank combat measured by seconds, this advantage meant survival. The Italian crew of the destroyed Semovente had possessed courage, training, and adequate equipment by Italian standards. They had positioned well, maintained their vehicle properly, and attempted to engage according to their doctrine. but they carried equipment designed under industrial constraints that Italy could not overcome, facing an opponent equipped with technology their industry could not match. The engagement lasted 20 seconds. The technological gap that determined its outcome had developed over years of divergent industrial evolution, doctrinal choices, and engineering priorities. American automotive industry experience, transferred to military vehicle production, delivered capabilities Italian designers could envision but never implement. The gyrostabilizer mounted in Morrison's Sherman tank represented less than 1% of the vehicle's cost. It added perhaps 2 hours to crew training requirements, but it provided tactical advantages that accumulated across thousands of engagements to help determine the war's outcome. Decades later, as combat veterans aged and historical perspective clarified technology's role in military outcomes, the Sherman's gyrostabilizer would be recognized as one of the war's most underappreciated technical innovations, not because it enabled revolutionary new tactics or decisively defeated specific enemy systems, but because it exemplified the industrial maturity and engineering sophistication that underlay Allied victory. Italy had designed the Semovente intelligently within severe constraints, producing a vehicle that served its intended purpose adequately. But adequate for Italian circumstances meant inferior to American technology in direct comparison. The manual fire control system, simple optics, and static firing doctrine reflected Italian industrial reality. They could not compete against American power-assisted stabilized fire control backed by decades of automotive industry experience. The contrast between Sherman gyrostabilization and Semovente manual fire control encapsulated a larger truth about technological warfare. Nations bring to military conflict not just the weapons they design, but the entire industrial and technological base that produces those weapons. Superior individual weapon characteristics cannot overcome fundamental industrial disadvantage when conflicts extend beyond brief campaigns. American industry's ability to mass-produce sophisticated fire control systems as standard equipment, train millions of soldiers to operate them, and maintain them under field conditions across multiple theaters represented industrial maturity that Axis powers could not match. The gyrostabilizer served as a small but clear example of this asymmetry. When American forces finally linked up with Soviet forces in Germany in May 1945, marking Europe's liberation from Nazi control, the Sherman tanks that rolled through devastated German cities carried the same gyrostabilizers installed in 1942. The technology had proven itself across 3 years of combat in every theater. Italian Semovente, most captured and operated by German forces after Italy's surrender, had been destroyed or abandoned. The survivors became museum pieces and scrap metal, artifacts of a different approach to armored warfare that battlefield results had rendered obsolete. The lesson would echo through subsequent decades of military technology development. Advanced fire control, whether gyroscopic stabilization in 1943 or laser rangefinders and digital computers in later decades, multiplied the effectiveness of average crews and allowed forces to fight successfully under conditions where simpler equipment would fail. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.